For thousands of years, humanity looked up at the night sky using only the naked eye. From the ground, the stars appeared locked in a fixed pattern, rotating like a giant dome around a completely stationary Earth. It made perfect, intuitive sense that we were the unmoving center of the universe. But there was a persistent problem in the sky. Occasionally, a few bright points of light, the planets, or wanderers, would break the pattern. They would slow down, appear to stop, and briefly travel backwards before continuing their normal path across the heavens. To explain this backward motion without abandoning a stationary Earth, Hellenistic astronomers devised a complex mathematical workaround. They added epicycles, putting the planets on little circular paths that constantly looped around bigger circular orbits. This system forced the geometry of space to bend to human intuition. Relying entirely on flawed human vision bred a kind of cosmic arrogance, allowing us to build a model of reality where the entire celestial apparatus existed solely to revolve around us. That illusion held until the turn of the 17th century, when pieces of precisely shaped glass were combined to build the first telescopes. Suddenly, a human sense had been mechanically extended. We could collect more light and see past the limitations of our own biology. When Galileo turned his telescope toward Jupiter, he noticed 4 tiny points of light hovering nearby. Over several nights of observation, he watched those stars rotate around the giant planet. He had found moons, celestial bodies that clearly orbited something other than Earth. This visual proof dissolved the need for messy, convoluted epicycles. The sky could be mapped cleanly and directly if the planets, including our own, traveled in simple, imperfect ellipses around the sunday. Earth was stripped of its special status. We were demoted from the anchor of reality to just another planet, tracing a path around a very average Sunday. By the late 18th century, astronomers like William and Caroline Herschel began constructing massive telescopes using polished metal mirrors. They attempted to map the exact shape of the Milky Way simply by pointing their instruments in every direction and counting the number of stars they could see. Their final map suggested our solar system sat right near the center of the galaxy, but their initial sample was critically flawed. Space is filled with incredibly dense clouds of dust that obscure visible light. The Herschels could only see as far as the nearest dust clouds, blinding them to the true scale of the galaxy beyond. It took over a century to correct this error. Astronomer Harlow Shapley realized he could bypass the dust by looking at globular clusters. These are gigantic, dense spheres containing tens of thousands of stars, and crucially, they hover far above and below the flat, dusty plane of the Milky Way. To measure exactly how far away these clusters were, Shapley tracked a specific type of star within them, called a Cepheid variable. A Cepheid variable operates like cosmic clockwork, brightening and dimming over a regular period. Because that stable pulsation tells astronomers the star's true brightness, they can calculate the exact distance to the star based entirely on how dim it appears through a telescope lens. Shapley mapped these pulsing stars and revealed the true dimensions of the Milky Way. Our solar system was nowhere near the middle. We are roughly 25,000 light-years away from the center, drifting on the distant, dusty fringes of the galaxy. In 1917, the technological frontier moved to Southern California with the completion of the Mount Wilson Observatory's 100-inch Hooker telescope, a massive 4-ton mirror uniquely forged from melted wine bottle glass. American astronomer Edwin Hubble used this new instrument to tackle a fierce debate dividing the scientific community. Were the glowing spiral shapes seen in the sky just local gas clouds within the Milky Way? Or were they separate, entire island universes located far out in the void? While comparing photographs of the Andromeda Nebula in 1923, Hubble identified the rhythmic dimming and brightening of a Cepheid variable star. When he ran the numbers, the math showed this star was located at least 900,000 light-years away. That placed it far beyond Shapley's outer boundary for the Milky Way. Andromeda had to be its own massive, independent galaxy. The known universe had violently expanded overnight. We were no longer occupying the only galaxy in existence. We were adrift in a sprawling void filled with billions of independent galaxies. But ground-based telescopes eventually hit a hard physical limit. Once its optics were fully calibrated, it began pulling in sharp, highly detailed images from outside the interference of the atmosphere. In December 1995, astronomers pointed Hubble at a seemingly empty, dark patch of sky near the constellation Ursa Major. The target area was roughly the size of a coin held at arm's length. They left the telescope's shutter open, collecting whatever faint light hit the mirror for 10 straight days. And the resulting image was truly astonishing. That tiny, supposedly empty void held nearly 3,000 distinct galaxies, showcasing a massive variety of shapes, colors, and ages. Because light from those distant objects takes millions or even billions of years to traverse the vacuum of space before hitting a telescope lens, observing the deep cosmos is a literal act of time travel. The deep field image proved we could look backwards through history, toward the very origins of the universe. Our eyes evolved to detect only a tiny sliver of the radiation traversing the cosmos. To truly understand the universe, telescopes had to be designed to detect the broader electromagnetic spectrum, tuning into invisible wavelengths, like infrared light. Because infrared radiation easily passes through dense clouds of cosmic dust, these specialized sensors allow astronomers to peer deep inside stellar nurseries and witness the formation of infant stars. Astronomers use the transit method to find exoplanets. This chart shows how a tiny, periodic drop in brightness occurs when a planet passes between the star and our telescopes. Continuously monitoring 150,000 stars, Kepler captured thousands of these transit signatures. Statistical math dictates there must be tens of trillions of planets scattered throughout our galaxy alone. We now know that solar systems come in a chaotic variety of shapes and sizes. Realizing we're just one rocky world among trillions forces us to confront our sample size and ask whether the liquid water on Earth is truly unique or just an ordinary drop in a cosmic ocean. To push those boundaries further, humanity built the James Webb Space Telescope. Operating 1 million miles away from Earth, its massive array of golden mirrors acts as an infrared time machine designed to capture the faint heat signatures of the very first galaxies forming after the Big Bang. Every new generation of optics delivers another harsh measurement of our true physical scale. We are on a tiny rock, orbiting a highly average star, tucked on a spiral galaxy's edge, amidst trillions of other galaxies. The majority of this unimaginable expanse is cold, irradiated, and aggressively inhospitable to life. From Galileo's lenses to the massive gold hexagons of Webb, our instruments have systematically stripped away our perceived centrality. We built machines that mapped reality, replacing human arrogance with a necessary, data-driven, cosmic humility. We are no longer the physical center of anything, but as we shrink against the vastness of space, our significance shifts. Our place in the cosmos is defined by the fact we are a species curious and capable enough to look up, build these extraordinary machines, and comprehend the infinite.